Welcome to the session 10A, electronic measurements. I hope you managed to sleep well last night because we have a very interesting morning ahead. So we have 6 speakers ahead, and I'm going to chair the session today. My name is Tomás Gómez. I'm from Spain, and you know that you have 15 minutes for presentation and Q&A. So we'll keep the presentation to 12-13 minutes, and after that time I'll make you know that your time is almost running out, so we have time for questions. So our first speaker is Shu. Sorry. And she's presenting a work entitled Wireless Feeding Rate Real-Time Monitoring System of Combined Harvester. Okay, thank you.
Thank you, Chairman, and good morning, everyone. It's my great pleasure to be here to do the presentation. The topic of my presentation is wireless feeding rate monitoring system of combined harvester. So firstly, let me do some brief introduction of combined harvester. It is a multi-function machine which can be efficiently used to harvest the grain crop. And the process has some problem. In a moment, sorry. Maybe we can see outside. Yeah. For this machine, it has a lot of different process for producing the grain. With this is the header of the combined harvester, and this part is the transport, and this is the threshing drum. The grain will be separated from this part with the straw, and for the bottom of this, it's a clean processing. After the clean processing with this part, it will collect the grain into the storage part. So this is the main purpose of the combined harvester. Okay. And for our work is to test the feeding rate, because the feeding rate is one of key operating parameters of combined harvester. The working speed and power consumption of combined harvester is depend on these parameters. It is very useful parameters for the driver to control the working speed of the combined harvester. In the past, there have two typical ways to test these parameters. One is to test the pressure of transportation bottom plate for this part, the transportation part. And another method is to test the torque of the threshing drum. For this is also in the past is very popular. But nowadays the combined harvester is use hydraulic system. So for this part and this part, they use a hydraulic system to control it. So it's difficult it don't have some sprocket. So sprocket way. So we can't use both of this method. So we try to test this part, the header, because the header also use sprocket wheel. So we will test the torque and the speed, the rotation speed of this part to get the feed rate of the combined harvester. So in our work, this is a picture of the header, and this part is auger propeller. This part is auger propeller. You can see this part. It's this part, yeah, inside. And in our research, we will install the sensors in the front of the combine harvester to get the speed and the torque parameters of this harvester. And we also developed the sensors and detecting system by ourselves. This is the picture of this. First of all, we have to get some mathematical model. So we, according the working principle of auger propeller, we get the relationship between the feeding rate and torque and rotation speed with these equations. After that, we have to, for this part, rotation speed is not difficult to test. Only with Hall sensor is okay. But for the torque, we developed the sensors by ourselves. As the spoker wheel has enough lateral resistance force, so we refit this part, the sprocket wheel, and it looks like this. To make it as an elastic element, and we paste the strain gauge into this part, and to build a bridge circuit. So this is the picture of our detection system, and with this system, it has 3 parts. One part is the power supply. It's very important. And another one is the bridge circuit and the signal conditioning circuit for this part. And this is our refit sprocket wheel inside. All for the torque signal, it will transmit by the Zigbee module. In the Zigbee module, we also apply. This is also we apply by ourselves because of our really request. And in this part, it includes the amplification and filter, AD conversion, and the Zigbee transmission module in this part. After the develop of these sensors, we do some laboratory calibration. And we get the voltage, the relationship between the voltage output and the torque. With this is a laboratory picture. And we also do the fire test in 2015 at Henan province. It's in the middle of China. This is the picture which we do the fire test. And you can see for this part, we install our sensors, detection system like this. This is for torque, and this is for speed. Speed is only if we use the Hall sensor is okay. And from this part is the testing flow chart, how to work. The fire test separated by 2 parts. One part is the celebration part. So for this part, we will do some exam to make sure the coefficient K and the coefficient F of this test. And after this, we will do the real fire test. This is the result. We choose 8 group. We totally we did 25 group. We choose 8 of them. With the analysis of all the results, the error range is between 0.55% to 6.68%, and the maximum test error is not exceeding 10%. So for us, it's okay. For the combine harvester, it's okay. It's not very high. So the conclusions. In this paper, we develop a new wireless detection method of feeding rate based on torque measurement of auger propeller is described. And our system includes two main parts. The strain gauge to measure torque of real-time harvesting feeding rate, and the wireless module which can be transmit the signal to our data acquisition system. And with the laboratory calibration and fair test, our system was verified. Okay, thank you.
We have time for a few questions. No?
Maybe just small recommendation. When you put the number of errors and you use 3 figures, it is maybe too much, because error is already shows that the level of confidence is so low that you should use maximum 2 digits in your error description. So just recommendation. So smaller recommendation.
Okay, thank you.
Thank you.
Thank you.
I have one question.
Please.
What is the frequency that you need to sample your feeding rate?
It's not very high. We will only set it 1 second. It's okay, not too high.
Oh, okay.
Yeah, because the speed of a combine harvester is also not too high. Almost 4 kilometers per hour, the highest.
Okay.
Yeah.
And what is the stuff that you are harvesting?
Yeah.
What are you harvesting? Is wheat or?
It depends weight, grain, and the corn. Now we also do a lot of work for the corn, harvesting corn. Yeah.
No more questions? Yes, I have another one.
Thank you.
And what is the use of this data that you get? If the feeding rate is too large or too low, what do you do then?
We use it for our, sometimes it will show for the driver. And if the feeding rate is too high, they will decrease the speed. Yes, because the threshing drum is very easy to broken. If it's feed in too much. So firstly, it's for the driver. Another is for our automation control system. With these parameters, we can do some automation system to control the different key components of the harvester. So it will not have some problem when it's working.
Okay.
Yeah.
Okay, thank you very much again.
Thank you.
And now we can go to our second speaker, and this.
Wait a minute.
This is a work into the metrological properties of a 2-output transducer for measuring sum and difference of small resistance, and it's presented by Adam Iczkowski.
Yes, Adam Iczkowski.
Thank you.
Thank you. Ladies and gentlemen, it is a group work of 4 authors from different departments. And my work will be connected also with strain gauge, like Xin talked something about strain gauge. My transducer also can be used for measuring strain. And this work is about, this is a continuation of previous works on transducers we've made with my colleagues, and we usually made some articles about Whetstone Bridge, Anderson loop, comparison of these circuits. We also tested current sources, thermal effects, and some unsteady states when switching over the current sources. And this will be to present a prototype of converter transducer. to output, to input, to measure small changes in resistance, to show some technical problems in realization because current source is pulsed and it caused some problems, technical problems. The circuit is more complicated, and yes, and of course to present some results, some parameters like nonlinearity error, sensitivity, resolution, maximal frequency of work, settling time, and so on, so on. So what do we measure? Firstly, we measure little changes in resistance in this range. I mean, we measure some of two changes in resistance and the difference of two changes in resistance. It can be strain gauges, two strain gauges, and as you can see, this difference can be positive and or can be negative also, because the range is plus minus 1 and plus minus 2 in fact. And the idea of this is to convert the changes of resistance into analog voltage, and then chart national instruments with parameters like this. And in this test I used two precision resistance Descartes boxes, not real sensors. Real sensors will be used in the future, but because of the reason is just resistance Descartes boxes, not are linear. And this is the scheme of preconditioning module. Here we have the sensors. This is 4-arm bridge. Here we have electronic keys like this. It's MOSFETs, and yes, and we used current source LT3092, but we also tested another current sources, and this presentation was on Monday about other current sources which can be used in this project. And the idea is to switch on and switch off the transistor keys, yes, and to measure two voltages on the diagonals of this bridge. And as you can see, the keys are quite fast. Rising time is in nanoseconds, falling rising time is in nanoseconds, and resistance of these switches are 1 milliohm, so it cannot influence on the resistance in arm bridges. This is control and output signals, control signals, output signals. The idea is to measure average of UDC1, UDC2, UAB1 and UAB2, but there is some problems. This is bipolar square wave, quite high amplitude, and just a little part of useful signal. So, and of course, this voltage depends on the difference and sum of resistances. So we should make a proper signal conditioning circuit. And this is just the first part, which is to create a reference voltage to convert differential voltage into single-ended voltage and to give it to the input of amplifiers, in fact, to amplifiers here. And these voltages from the diagonals of the bridge are amplified, firstly by differential amplifiers and then by instrumental amplifiers, and gain is in this range. What is for generally this complicated, maybe complicated circuit? It is just for giving zero voltages on the output when the increment changes in resistance are zero. And if we do this, the gain can be higher and the resolution can be bigger. And but it is not so, how to say, ideal, because if we have a current source and current source it is switched, we have unsteady states, and amplifiers get in saturation state, and it takes time, of course. Amplifiers are saturated 120 microseconds, and fall time is longer, is 300 microseconds. So in fact, if you sum up, it is about 500 microseconds. So we should wait that time and then give it to a DC converter, for example. So this is a timing diagram, and that's why, because of these unsteady states and saturation and so on, we introduced a time delay. A DC converter waits 1 millisecond and then sampling and convert the signal. And that is a practical realization in DIN rail box. This module consists of power supply because we need a bipolar supply for amplifiers, for example. So we have a DC-DC converter here, and this is this metrological part, these two channels, potmeters, amplifiers, and so on, output, inputs, and what about the results? These results were made in different situations where two resistances were increased or decreased, one increased, one decreased sometimes. And by analyzing all these situations, cases, maximal error, maximal difference, nonlinearity error was about 0.08 ohms. Relative, it is less than 5%. Resolution, sensitivity. Resolution is 0.001 ohm, and sensitivity is 1.5 ohm, volt for ohm divided by ohm. And the big problem was noise filtering. We used I didn't show on slide filter because I placed a simplified circuit, but we used low pass filters between output of bridge and first amplifier, and that reduced noise from this value to this value. Yes, maybe 4 times. 4 times. This is a noise in peak-to-peak values. Yes, peak-to-peak values, and so we used also shielding. We shielded all the circuit by cables, and this reduced slightly also this peak-to-peak noise. So we needed finally to make software averaging of these results, and then the noise is very good. It's 2 millivolts peak-to-peak, and can be used. The signals can be used, and it is thermal tests. This is, I think, one of the hardest things in all of this, because the module self-heated because of this DC to DC converters, power supply, and about 10 Celsius. So we need to wait 10 minutes for warming up, and then if it is in steady state, when temperature is steady, we also measure drift, zero drift of bridge, and this zero bridge was quite good. It was 0.25% of range. To summarize this all, yes, in this table you can see the parameters of this transducer. We also checked settling time during two resistant change 1.01 ohm. It was 15 milliseconds. What I can say, it is quite complicated construction, because we have here bipolar supply, this switched current source. Every current source is useful to this project because of its dynamic parameters. And yes, this maximal frequency of switching is limited by unsteady state of output voltages, and of course using DC current source or DC voltage source, probably the circuit is much easier, but the results also. Thank you for attention.
Thank you very much. So we have time for a couple of questions.
When I look on your, thank you for your presentation. When I look on the noises, because maybe this is something what could be for me interesting, I see like two components, frequency components. Have you made any analysis of the sources of this noise and what is the spectrum? Because it looks quite deterministic in some way.
Yes, I think it is radio frequency noise, of course, and it is low frequency noise in general, and we even add we made such a box from Caprum and added on the top of this PCB and shielded it also, because yes, many random noise influence
location.
Yes, electromagnetic interference, radio frequency interference, because the changes we measure very low. Yes, so all of it has influence.
But at least in this picture that you show, it seems to be that there are two main components of the frequencies, so maybe it was interesting to analyze which peaks of the frequency you could get.
I didn't do the tip, but I tried to just limit, just to limit, used filter, then shielding, then software averaging. It's also filtering, yes.
Do you expect some nonlinear behavior from real sensors?
Yes, I think because if we have, for example, strain gauges, we glue it to any surface, and there is some nonlinearity caused by this. If we stretch and compress, that's why I used the cut boxes, because I would have nonlinearity of sensor and nonlinearity of circuit, and I would not make any conclusions.
And do you think you can cope with this nonlinearity with this device?
Yes, probably. Maybe this. Usually, if we have in classic metrology, yes, we have Whetstone bridge and quarter bridge, for example, half bridge, and sometimes we can compensate nonlinearity of sensor with nonlinearity of circuit, yes, and this final, how to say, final line is more linear.
Okay, we can thank the speaker again. Thank you very much.
Thank you.
Our next speaker is Stu. Monsieur Craig. Yeah. Okay. And he's presenting a work entitled An Empirical Methodology for Power Analysis of CMOS Integrated Circuits. Okay.
So, good morning, everyone. My name is Momčilo Krunić, and I'm coming from the RTRK company from Novi Sad, Serbia. Today, I would like to present my research titled An Empirical Methodology for Power Analysis of CMOS Integrated Circuits. So, the most interesting aspect of this research is that provides the direct link between the highest level of abstraction, such as instruction, back to the lowest level, such as CMOS transistor. Context of this research is embedded processors, software development tools, and all that integrated into the integrated development environment based on Eclipse RCP. Used for programming target platform. And this is one of the views from the IDE that inspired this research. You can see that it shows a core activity graph during firmware execution. So the main question was that inspired this research: can we extend this view in order to provide information about the energy that is being consumed during firmware execution? So, in order to answer that question, we have to decompose energy dissipation to base components, and those are static energy dissipation and dynamic energy dissipation. And dynamic energy dissipation can be from active peripherals or DSP cores, and DSP cores dissipate energy while running in idle state or executing instructions. And if instructions are being executed, we can divide base costs and inter-instruction effects. I won't go to details in those components. That is not the focus of this presentation, but I just want to emphasize that those are the base components, so everyone should be aware of. So this slide shows how energy is related to the size of a process node. You can see that decreasing the size of process node, actually we are increasing dynamic and static power that are being dissipated. Actually static power even more than dynamic. From the table we can see that on 90 nanometer process node, when we decrease process node to 45 nanometers, dynamic power per square centimeter is increased twice, and static power is increased 6.5 times. So meaning that decreasing the process node, static power becomes dominant component of dissipation. This slide shows energy dissipation during one clock cycle, and we can see that surface of blue rectangle represents dynamic energy consumption, and you can see that this surface is constant over the time, meaning that dynamic energy dissipation is constant. It does not depend on clock cycle. On the other hand, we can see static energy consumption, which is red surface. That we can see that static power dissipation is constant over the time, which is actually the height of that red rectangle. Those are some main properties of those components, which will be used further on during experiments. So on this slide we can see just the main components of leakage current represented on CMOS inverter. There are actually 4 components that building leakage current, which is the main reason for static dissipation. And we can define leakage current of CMOS integrated circuits as sum of leakage currents of each individual CMOS transistor that is under the voltage supply, and therefore we can also define static power dissipation as well as energy that is being dissipated during one clock cycle. Also we can define, we can see that dynamic dissipation is created when we have changed input state of the CMOS transistor, and we can define that dissipation as a multiplication of equivalent capacitance, which is being charged and discharged during those changes, and voltage supply on square and frequency. So we can define dynamic dissipation as a sum of all of each individual dynamic dissipation of CMOS transistors, and this is the most important contribution of this dissipation. You can see that is a sum of each individual equivalent capacitance, and we can define that as effective capacitance, which means that is the actual capacitance that being charged and discharged during one clock cycle, and that can be used as a quantitative measure of energy, dynamic energy dissipation. So in order to identify which is the dynamic and which is static dissipation, we can use properties of those dissipation that I have mentioned on the graph that have red and blue surfaces. So we know that static dissipation does not depend on time, on period of clock cycle, so we can use that property in order to identify leakage current. So based on that property, we can create 2 equations in order to identify which is the part that does not depend on clock frequency. So we have one equation and the other. So we are actually performing measurements on different clock cycles, and then we are calculating leakage current. And this is the outcome of that experiment, and you can see that relative standard deviation is around 0.5%, which means that we obtain pretty reliable data. On this graph, we can see the power dissipation. That is power, not energy. So the blue rectangle represents the overall power dissipation, the red one represents dynamic power dissipation, and the green one is the static dissipation. You can see that on different clock cycles the static energy dissipation remains the same, but dynamic dissipation is decreased, because when you decrease the clock frequency, you decrease switching of activity on CMOS integrated circuits, so that is expected behavior. So, on the other hand, if we observe energy that is being dissipated during one cycle, we can see that that dynamic energy dissipation is constant over the time, but static dissipation is increased as we decreased or we increased the clock period. So that is also expected behavior. So based on those two graphs, we can make two conclusions: that when core is in idle state, the frequency should be clock frequency should be decreased as much as possible in order to reduce switching activity, therefore dynamic energy dissipation. And on the other hand, when core is in execution mode, while executing instructions, frequency should be increased as much as possible in order to reduce static energy dissipation. And this is a table of 5 cores that we have on our target platform, and effective capacitance that we calculated. So this is, for example, effective capacitance of microcontroller while running in idle state, meaning that this is the actual capacitance that is being charged and discharged during idle state of microcontroller. And we can make some conclusions based on this. This can be very valuable for firmware developers when we make instruction set energy characterization, meaning that each individual instruction is tagged with its own energy dissipation. Also, inter-instruction effect could influence instructions scheduling during firmware development. Very also significant could be power-aware compiling, meaning that the compiler as a tool could use those empirical data in order to generate more efficient, energy-efficient code. And firmware developers will have feedback about firmware application energy consumption, meaning that they can maybe create more energy-efficient firmware solutions. And also various tools could be developed to make some hints to developers in order to make a more energy-efficient firmware solution. Thank you very much, and if you have any questions, I will be glad to answer.
Okay, we have time for a few questions.
Yep.
I have one. When you separate dynamic power consumption and static, then it could be probably that dynamic consumption depends also on temperature, and when it influences the static consumption. And did you consider this?
We actually didn't consider that kind of influence on this research, but maybe that could be interesting in the future experiments. but we didn't have that kind of observation during this research.
Okay.
Yep.
You title your presentation analysis, but I think that the final, let's say, outcome of this research should be some kind of heuristic model, you know, because you search for some pattern in the behavior.
Yeah.
So what you show as the results, I think that is possible to find some, let's say, equation or let's say model as the final, because this measurement, I can see already from this that it's possible to in some way
That is, yeah.
find some pattern. So I would recommend you to summarize it as equation dependent on frequency or some others.
That is quite correct. This is actually just part of my PhD dissertation. So the whole research contains those equations. So like dependent on effective capacitance, frequency, and voltage supply. So equation evaluates power and energy consumption during firmware execution. So that is like the final outcome of this research.
Because analysis is not the goal.
Yeah.
The goal is the modeling.
Yeah.
So let's say this is the tool to find the pattern.
Yeah, and this is this measurement that I have shown here. It's I have wrote a patent for that also in Serbia. So that is kind of part of the whole picture, and not the whole, but I have those equations that evaluates energy consumption.
Thank you.
Okay.
Thank you.
Okay, thank you very much. Okay, our next speaker is A. Riedel, and he's presenting work entitled Comparative Measurement of Cardiac Cycle by Means of Different Sensors. Okay, you're welcome.
Hello, my name is Heiko Priidel. I'm a PhD student from Tallinn Technical University, and I'm presenting part of my PhD research work, which is actually related to detecting hematomas and cancerous areas from human brain. So a few words about motivation of my work, about ultra-wideband radar working principle, which is a main device and method for detection of the tumors in the brain, and problems related to that kind of measurement, and then about multi-sensor measurement device, which is designed to understand actually ultra-wideband radar signal sources, and a few words about current results. So ultra-wideband signals for medical diagnostics are under development already quite a long time, over 10 years. And recent developments in component base allows to actually implement them also in real hardware. There are numerous studies about signal sources of ultra-wideband radar device, and there is still dispute about where actually signal is originated from. Some research group claiming that signal actually is coming from surface of the patient skin, and another opinion is that signal is originated from the internal organs or tissue layers. But there is no clear understanding about real situation. So a few words about ultra-wideband signals and radars. Conventional radars are using a continuous wave, like CW radars or Doppler radars, generating a carrier. And reflection from the object will be then detected and analyzed. Ultra-wideband radar works in a different way. Instead of generating a carrier, we are generating single impulse, as short as possible, and generating that kind of impulse typically in a range of tens of picoseconds up to hundreds of picoseconds, is leading to spreading impulse energy to a very wide frequency range. Allowed range for ultra-wideband radars is 3 gigahertz up to 10 gigahertz, so all the energy is actually spread on a very, very wide frequency range. And receiving the signal is actually working in a time gating receiver principle, that we are generating impulse. This energy is transmitted through the antenna towards to the object. Part of the signal will be reflected back, and here we have a correlation receiver which is capable of actually detecting signal very precisely in a spatial dimension. So we can detect the actually area where the signal is coming from. And reflection from the object is happening because of the electrical properties of the different tissues. So part of the signal will be reflected back in a tissue layer boundaries. So in case of measuring, for example, heartbeat signal, when we are transmitting energy, we will get first reflection from the air skin boundary, second reflection from the fat muscle, and finally some reflections from the heart. And because of heart is moving, we can detect signals. Unfortunately, signals are attenuated very much. For example, 10 gigahertz signal will be attenuated over 200 decibels or even more. So there is questionable if we really can detect signals from the heart wall. From this graph, you can see that different reflections from different tissue layers, skin, fat, muscle, cartilage, lung, and finally from the heart and blood layer. So the signal is attenuated like 10 minus 100 decibels. And what kind of this radar is detecting, what kind of signal it's detecting. So we can see this phase breathing was hold, so we can see only a heartbeat signal, and there is following one deep breath cycle where we can see also basically moving of the chest, and then on top of that heartbeat signal. Now, where those signals are actually originated. Heart movement is a main source, of course. Sorry. And now we have several possibilities why we actually get that signal back. One possibility is blood perfusion on the skin, because of amount of blood is changing in the skin. Reflection coefficient is changing, might be also antenna coupling changing, and this will generate the signal. Another possibility is inside body organ movement, which will lead to skin movement. So there is possibility that we actually not measuring the heart itself, but moving of the chest, which means that it's purely mechanical movement. And Then echoes from internal organs, antenna coupling, far field, near field coupling, black body radiation, and sources like that. So there is probably many possibilities, but where the signal is really coming from is still not 100% clear. So part of my research, I developed a small device to measure actually how much possibly signal is coming from movement of the chest or from the blood perfusion from the skin. So this device was attached to the body with a standard EEG electrode attachment, and we measured the heart aortic valve acoustic signal, movement of the skin in means of acceleration sensor, and optically we measured also amount of the blood in the skin in the means of reflection coefficient of the skin itself, which is basically a reflectivity test in IR and red light range. Measurement setup was set up like patient was sitting in a chair. We had ultra wideband radar transmitted signal and measured it through the national instrument ACU card. Then we had a multi-sensor measurement device which measured the acoustic signal, skin perfusion, and chest displacement or movement, which was also lead to the duct card. And for a reference, we measured the ECG signal, and so main goal was to put all these signals to the same timeline, so that we can compare actually radar output signal with physiological processes, and possibly compare it with multisensory measurement signals to verify how phases are shifted that related to heart movement or skin perfusion signal, how radar output signal is actually changing, and is there any correlation between them. So few signals are still process is ongoing, few signals are still not measured, and this device will be developed further. Also analysis is not finally yet done, but if you look radar output signal compared to the ECG signal, we can see radar minimum, radar signal minimums exactly the same time as ECG signal is appearing. And if we look now radar output signal or chest displacement signal compared to ECG, then we can see that chest displacement actually is not in the same time as ECG, so, and not the same time with the radar output, which can show that signal source is coming somewhere else. There might be some part of signal from actually chest movement, but there is still possibility that part of the signal coming from the deeper layers. And another interesting result was blood perfusion signal, and actually the signal change is very low. It's less than 0.1%, which showed that the probable source skin perfusion as probable, blood perfusion as probable source for the radar signal is also unlikely. That which also supports the idea that the signal is still coming from internal layers. For conclusion, this multisensory device was developed, and the preliminary tests and experiments were conducted. Results showed that probably signal source is not only the skin movement or body or chest displacement signal, but we have to analyze it further. One idea is to actually mechanically restrict chest movement and try to measure radar signal this way that chest can't move. And we have also idea to add bioimpedance measurement channel here to also correlate signals with bioimpedance measurements. Thank you.
Thank you very much. We will run out of time, but there is one short question.
About UV radar, did you buy some solution or you make it by yourself?
This was our own development.
Yes, okay. Thank you.
Okay, thank you very much. Our next speaker, Wojciech Oliva. Yes. And he's presenting a work entitled Fast and Accurate Frequency Meter using the interpolated DFT method.
Oh, good. I check it when I load it. I don't know. Sorry. I'm not used to
No,
this.
the one to the right, the one you have tried just to the right. Yes, this one.
Oh, okay. Thank you. I've done it with a very old version of PowerPoint, and I'm not used to the newer one. Okay. Sorry for that delay. I want to show you my and my colleagues' work on the frequency method that uses interpolated DFT method. First, I remind you or introduce you interpolated DFT method. If using only discrete spectrum obtained after making DFT to estimate frequency has a very poor resolution. Simply, it is only the index of the maximum point of the spectral line. But, as you can see, the shape of the spectral line still have information about the true frequency of the signal. And interpolated DFT methods, because there are many of them, simply use two or more greatest points to calculate that displacement from nearest integer. Some years ago I introduced my own version of interpolated DFT method, and it is so simple that you can see all of it on that one slide. It uses 2 maximum points. It depends when it is point with index L, and L plus 1 is bigger than which is bigger, L plus 1 and or L minus 1. So it has 2 versions, but they are very, very similar. It is quite amazing that these simple equations could lead to estimation of frequency with very high precision. If we define the method gain as how many times the estimation frequency is better than using only discrete spectrum, then this gain could be either hundreds of thousands. And after some articles that I have written, in which I analytically do some analytical assumption about properties of the method and make some simulations, the question arises if these properties will occur in real environment and reality. So we decided to, with my colleague, to build as fast and as accurate and as simple frequency meter as we could. We choose 32 bits Atmel microcontroller with DSP and floating point units inside, external fast 14 bits analog to digital converter and some other elements. And the prototype was built. To check the properties of the device, we use signal generator Fluke 6080A, which produce very stable and spectrally pure signal. The measurement procedure wasn't so simple that let me introduce some terminology. First, device acquires series of samples, voltage series of samples. Then FFT is made, digital spectrum is obtained. After using interpolated DFT method, the frequency is estimated, and many such estimations forms a set of frequency measurements. So we have 2 different samples, voltage and frequencies, and 2 different series, but first I will call always series, and the last I try to not forget to name only set of frequency measurements. First, let me show you the most basic properties of the matter. Simply, steady signal with frequency 1 megahertz was coupled to the input of device, and this is set of frequency measurement. Very normal look. Histogram of that set is shown here. It has the shape which is similar to Gauss. This was done for the FFT size 1 kilo samples. I didn't tell it, so I come back here. FFT size is the number of samples in voltage series. Sorry. On the next slides, the only thing that is changes it is FFT size. For bigger FFT size, we have the signal with lower lower noise, and the histogram is more narrow. The same is for 4 kilosamples in FFT size 4 kilosamples. I have had to change the scale because it will look like a clear line almost. And the last one, FFT size equal to 8 kilosamples. And histogram consists almost only of four elements. Let's summarize these main properties of the matter. As could be expected, the best estimation was achieved for the greatest FFT size, and in contrary, the highest frequency rate of frequency measurements was achieved for the smallest FFT size. But there is one more interesting result. It is method gain for 4 kilosamples, which is bigger than for 8 kilosamples. Let me explain it one slide later. First, I want to show you the influence of noise on accuracy of frequency measurement. It is well known that estimation of parameters of signal that is influenced by noise has some limit, that it is known as Kramer-Rao lower bound. For in situation when known of three sinusoidal signal parameters are unknown, the limit of such estimation of frequency is given by this equation. Sometimes ago I derived the equation, the limit, for my own version of interpolated DFT method. Both relations are drawn on this picture. There is drawn also measured values, and something strange happens here also, because for signal to noise ratio greater than about 25 decibels, the accuracy do not increases with increasing SNR. That two strange observations led us to suspicion that we have problem with using mathematics, with using single precision floating point format. And indeed, if we look more carefully in some histogram, it could be seen that the difference between neighboring points has only two values, which is one time and second time by the smallest one. We of course were aware that single precision floating point format has a limitation, but I must honestly say that it was for me something surprising that we achieve the delimitation as easily. Let's look at other sources of errors of interpolated DFT method. the stability of or instability of input signal is such source of error. When we try to model the variation of input signal amplitude during acquiring process, it could be done in the simplest way by using amplitude modulation. In such case, the systematic error depends on modulation index. On this figure it was 0.4, modulation frequency, and the modulation phase. It could be seen that the greatest systematic error occurs in this region. So we choose to try our device in such condition that we cutting this feeder on this region, and the comparison between analytical predictions and measured values are shown on these pictures. The last influence on accuracy of frequency measurement was frequency variation itself on when the samples are acquired. But it could be easily seen that if we have sampling frequency, it behaves like sampling anything else, and it must obey Shannon-Nyquist theory. So if we have a small rate of changes of frequency, we simply see it in set of measurements. When we
should jump to conclusion.
Okay, it was only one. So our method was fast and accurate. We find new limit caused by using a single precision floating point, and that's all. Thank you.
Okay. Okay, we are already on the time of our next speaker, so I think it is not fair for him. So if you have any question, you can ask him later, I think. Yes, okay. So thank you very much. So this is our last speaker. He is Margus Messheim, and he's presenting a work about realization and evaluation of the device for measuring the impedance of human body for detecting the respiratory and heart rate. Okay.
Thank you, Mr. Chairman, ladies and gentlemen. My name is Margus Messheim, and I'm a BSc student at Toomas Johan Seebeck Department of Electronics at Tallinna University of Technology. Today I will speak about my work in the field of measurements of electrical bioimpedance and present a device for monitoring the cardiac and respiratory activity. The title of the presentation is the realization and evaluation of the device for measuring the impedance of human body for detecting the cardiac and the respiratory activity. Firstly, a short introduction. Outline. Firstly, introduction, and then the idea and realization of the device. Then shortly about the methods and measurement setup. Then I'll share the results with you with the focus of breathing and heart beating, monitoring these processes. Then shortly the conclusions and show you a bit of my future plans. Okay, introduction. The monitoring of vital signs has become an important topic in personal healthcare. The reasons are the popularity of smartphones and its accessories. This has happened through the development of technology and the interest to personal health. To gain access to these processes, there are variety of methods available, from which in current presentation the electrical bioimpedance is used. Electrical bioimpedance, or EBI, is a tool that is used to describe the properties of biological organisms. And it is done in a way that an electrical stimulation is applied to the object, and its response is monitored. The fact that the processes of breathing and heart beating are variable makes it possible to follow this inhalation and exhalation and pulsating blood in the organism. The choice of the method is one side of the coin. Another side is the development of capable devices able to monitor the vital signs in real time. What is the key issue in developing the wearable devices is the contact interface with human body. Traditionally, in personal heart rate monitors, the direct contact is used. This presumes the direct contact of the electrode to the skin surface, and this is not always visible and not always comfortable. Then the capacitive connection proposes an alternative. Nevertheless, proposing new problems and issues, mostly in the fact that there will be a motion artifact. In today's presentation, the idea and evaluation of a custom-made measurement device for monitoring the cardiac and respiratory activity is presented. So firstly, the idea of the device is to apply a certain signal onto the object and measure the real part of the total impedance in two electrode configuration. The excitation signal is generated by oscillatory chip. It is a square wave signal of adjustable frequency. After the measured signal, the object is passed through inverting amplifier and is synchronously switched. After that, it is integrated and bandpass filtered. And for making it visually available on the screen of oscilloscope, it is amplified and low pass filtered. Here is the picture of the device and the method and the setup. Measurements were carried out to evaluate implemented measurement device for monitoring the vital signs, breathing and heart beating. We used a single volunteer and dynamic bioimpedance reference device designed in our institute. We used 3 different electrodes, traditional ECG electrodes, large foil surface plate electrodes, and textile electrodes of stainless steel yarn. And excitation signals above 2 megahertz were used to focus on the capacitive connection. So firstly, the results of the measurements on this dynamic bioimpedance reference. This device enables to adjust the imitated variable impedance of human, to adjust the parameters of respiration and heart beating. It was directly connected to the implemented measurement device. And it can be seen that in the cases of 5 megahertz and 20 megahertz, the result is the amplitude of breathing is most clearly detectable. Secondly, the ECG electrodes, they were positioned on the body to cover the full trunk. And it can be seen that breathing is available. Cardiac activity cannot be seen from this raw signal. Next one is by using these large foil electrodes. They were attached onto the outer surface of the shirt. Here can be seen the photo. And they were positioned onto the shoulders, sides of the body, and back side of the thorax, not on the front side. Two different electrode placement configurations were used. First one was covering the trunk vertically, and second one covering it horizontally. And results show that the respiratory activity is available in the cases of both configurations. The cardiac activity can be assumed to be available in the case of first configuration, the highest excitation frequency, black line. Secondly, with the same electrodes, but directed to follow the cardiac activity. So they were positioned on the upper arms and the chest to get access to the subclavian arteries and veins, and to the heart. And it can be seen that the respiratory activity is available, but cardiac activity cannot be recognized with full certainty. And finally, the textile electrodes. Single configuration was used to cover the full trunk, and the electrodes were connected by using conductive thread. And can be seen that respiratory activity is available. The cardiac activity can be assumed to be available in the case of highest excitation frequency, the black line also. To follow the measured waveforms in the same, measured on the same frequency, this kind of graphs were created, and it can be concluded that cardiac activity is not available in the case of the three chosen lower frequency setups, but it can be assumed that it is available in the case of this 20 megahertz excitation frequency. And in the case of 10 megahertz, the amplitude is about twice lower than in the case of other setups. So the numerical evaluation reveals that the highest amplitude of signal is gathered in the case of this electrode shirt number 1, where the large surface plate electrodes of foil contact surface were used. And in the case of 5 megahertz, the highest value achieved. In the case of contact electrodes, it's more than 4 times lower when compared to this ES1 result. Now, concerning the cardiac activity, it can be assumed that the filtering can reveal more data. So this is here is the raw signal, and now here is bandpass filtered, post-filtered later in lab view, which incongruously gathered ECG signal. Typically, the human heart beats 60 to 100 beats per minute, and 12 to 18 breaths per minute. So this makes about 5 to 8 heartbeats per one cardiac cycle. So it is so available here as well in this count. And concerning the spectral analyze, to see if we can follow the cardiac activity also in this method, the fundamental signal of respiratory activity is clearly available. So this is in logarithmic scale and this is not. But the cardiac activity cannot be recognized from the noise. So this spectral analysis does not support the assumption that it's visually available. So to conclude, the design of the wearable device has enormous effect to the result of the measurements of vital signs. The respiratory activity can be assumed to be available from all of the experimented excitation frequencies and configurations. the cardiac activity seems to be visually available in the case of highest excitation frequency, but nevertheless the spectral analyze does not support this, and the analyze and processing of the signal can reveal interesting data concerning the cardiac activity especially. So a bit about the current work and the future status. We are focusing onto the complex solution as the motion artifact, which we are not considering in this study, has an enormous effect. So we are planning to add the coils, for example, into this integration into the clothing or garment elements, to have another method following the vital signs, or following the distance between the coil or the electrode and the body surface. And the future work is to redesign the device, bind the complex device, incorporate into the clothing, and also make cooperation with competence in textile design. Thank you. Here are my contact details. So, any questions? You can send me after.
Thank you very much. Of time for a couple of questions. Have you been considering other techniques for those parameters measurement? Because I was amazed, and even one of my students was excited, and he did the investigation. There is a technique when the measurement of the breath and heart rate and even the saturation of blood is based just on simple video. By looking into correlation between frame to frame into tiny differences, you can tell the breath, the heart rate, and etc. etc. Or you can take the photoplatismogram. If it is red and infrared, you have one information. If it is red and green, you have another information, and so on and so on. Have you looked into other techniques?
Thank you for the question. Yes, photoplatismograph typically presumes the device that is attached onto you somewhere. Yeah. We are aiming to the device that is incorporated in some kind of clothing element, which is hanging freely on you. Well, typically, the sportsmen maybe have these tight-fitting shirts and pants. We are aiming to some regular shirt that you can put on and it is unnoticeable. And yes, video is another option, very widely investigated, but the same issue. To integrate it into the clothing. So what we have tried is magnetic induction. So I mean the coils, single coil solution. It is another possibility to integrate into the clothing.
Okay, so the answer is no. You did not.
We have tried this magnetic induction. That is
okay,
the
but
other
I did not look into
but not the ones that you were saying.
Then another question comes from this. It is good that you are trying to devise some parameter which will indicate the quality of what you are getting. But don't you think that noise also has to be included? Because you are measuring just the amplitude. You are missing the amplitude, I can increase the amplitude.
In this case, yes. This is the initial study of this prototype of the device, and that was the way how we evaluated the availability of these vital signs that we are interested in. This is the current state.
But the signal noise ratio is high. I can increase the amplitude as much as you want.
Yeah.
And I will support you. My proposal is to use signal noise.
Yeah, I agree, and thank you for this comment.
Question? Just one. Did you actually measure the electrical impedance of the body? Because this was on your title. Do you have a measurement of the impedance of the body?
We measured the output voltage. We did not calculate the impedance. That. Yeah.
So you don't know how much the impedance is changing?
No, in numerical value, no. Yeah, we didn't do the calculation.
Did you consider that you can get some kind of information from that?
Yeah. this should be definitely included if the device is.
You are even
Yeah.
throwing away the imaginary part.
Yeah.
Maybe this can be.
Yeah.
Okay. This was our last speaker, and now the session is finished. So thank you all for coming, and thank you to the speakers, and thank you to the audience for the questions. And we can thank you all once again.
Me, because about organization. Okay. I am Alexander from Tallinn University of Technology, Estonia, and I should be the chair of this session. And let's do in such a way that, no, it means that my work is to follow the time of presentation. For every presentation there is 15 minutes, including questions. It means that it depends on you. Would you like that somebody asks you or not? Because we have to leave some time for questions. Okay, and let's do in such a way that when it's left, let's take 3 minutes to end presentation, then I will be in stand position as now. When we have time, I am sitting. Okay? And now we have the first presentation. I ask all of you to present your co-authors and so on, to make some introduction about your work, because I have no any information, only this booklet itself. Thank you. Let's begin.
Sorry for interrupting you at the beginning. My name is Kazimieras Bogdanas. I come from Kaunas University of Technology, and I'm here to present you a paper on a convergent distributed positioning algorithm for Internet of Things. It was co-written on me with Nerijus Jusas and Algimantas Venčkauskas from Computer Department. This is basically a project aimed to develop an authentication method, multimodal method for Internet of Things. So the outline of the presentation, I will describe you the motivation for this research, briefly describe the current use techniques for positioning in Internet of Things, or in general indoor positioning. I will describe the algorithm. I'll show you our simulation and its results. This is fairly simple idea, so I don't think it will take much time. We can skip over simple ideas. So, the general motivation is to create a multimodal of the identification authentication method for objects in the Internet of Things. Reasons for that is basically, there are a couple of reasons. First of all, you want to know the sensors you're getting data from are true. So for example, no one has swapped the sensors, no one is fudging the data, so in Internet of Things, you want to have some verification. And location can be one of the variables you can use to establish the validity of your data. Additionally, you might be interested in the data from only certain region, or let's say you are in underground sewers and you are interested in collecting toxic gas, for example, amount of toxic gas, you're interested in certain areas and you want to make sure that your sensors are in that area. So localization is actual for these problems. And of course there are huge problems with radio frequency based positioning if we don't have access to GPS or Galileo or GLONASS, satellite-based navigation systems. So whenever we have a roof over our head or attenuated signals, and especially with Internet of Things very cheap sensors, we basically have no access to this information from satellite-based positioning information. So that's why a lot of research has been involved into indoor positioning or positioning for Internet of Things. The main approaches to solve this problem, first is the received signal strength, and right now the conclusion is if anyone advises you to do something with received signal strength, you should smile and back away from that person, because it's not really useful unless it's kind of proximity indication. Then we have angle of arrival, but for angle of arrival we need more sophisticated antennas and signal processing. So for Internet of Things, this one also kind of not really applicable right now. Then we have time of arrival based estimation and measurements, and these can be differentiated into basically time of arrival when you just measure and have synchronized time around throughout your whole network. But for that you need really good clocks, so basically atomic level MEMS clocks, which cost in order of tens of thousands, hundreds of thousands, so not applicable again. Time differential of arrival also requires clock synchronization, even though locally, but still is a problem. And one of the approaches which is feasible, it still has its own problems, is round trip time. It's basically when you send a packet to between two network nodes, it is being returned, and then you divide the time which the packet traveled minus the time when it was being processed. So this can produce sufficiently acceptable results. Of course, we need a better hardware for that still, better clocks, but this might be feasible in the future. And positioning can be done in the network in several fashions, and combination of those. First is centralized, decentralized, and ad hoc. The centralized has issues because you need to, when the solution is being computed for every user as a centralized location, you basically need to transfer all the data to the center. It has to be processed and sent back, so you have network overhead, more energy requirements for these. However, the nodes themselves can be much simpler. The decentralized and combination of centralized is probably the most promising approach, also with increasing computational capacities of nodes. And it allows us to create this ad hoc network by adding additional nodes to it and having it expand in natural fashion. So we are basically aiming for round trip time, ad hoc, decentralized solution. For our algorithm, I would like to define several ideas and define different network nodes. So the first one, network node, which we are talking about, are the stationary network nodes, so the ones which are fixed in location. Then the user nodes are the ones which can move through the network and communicate with the network nodes. Network nodes between themselves also create an ad hoc network, so they are able to communicate. If they are able to communicate, they are able to perform range measurements. So that's good for us. Local reference frame is a term basically for us to use to create to compute position in very small local area between four network nodes. Absolute positioning solution is a solution which incorporates global navigation satellite system coordinates, so basically the GS84 or any other kind of global coordinate system. Virtual network node, I'll elaborate on this one a bit further. Out of time. So, and network convergence is an event when the network accepts absolute positioning systems. So the first thing what we suggest in doing is basically try to form the most primitive geometrical structures in the network. If we have 2D network, that would be triangles. In 3D case, we are looking for tetrahedrons. So basically what we do is for every node we create a local reference frame with coordinate systems at the beginning of the node 1. Then we choose second node, very primitive ideas, but we choose second node on the x-axis. It's a third node which is lying on the plane between x and y-axis, and that forms a triangle for us. So the last rule which we need is basically that our fourth node should not be on that plane where triangle lies. If and all these vertices represent communication. So if all these four nodes can communicate in between them, we can form a tetrahedron, and then we can compute a relative positioning between them. So just using simple trilateration. When we do that, we do it not for only one of these, but for every point we search for as many tetrahedrons as we can form. When we do that, we can accumulate them, aggregate in one local reference frame. there is no point in expanding it by trying to combine between two different nodes, because if you do that, you need to perform rotations. So, because the directions of local reference frame axis are accidental. Basically, it depends on what is the second node which you choose. That will be the direction of x-axis. So they are accidental. And if, according to distance, how far these nodes are, the farther the way they are, the bigger error is introduced when you apply rotations. So that's why we skip the rotation altogether and we just stay with the local reference frames. And we form a network of these local reference frames. Now, because these local reference frames are overlapping, we can basically map from one coordinates to another seamlessly during this performance of our simulation. So the next step is basically trying to obtain absolute positioning system solution and integrating it into our network. It is done by having user nodes which are global positioning, which have global positioning solution, some kind through, let's say, GPS unit. And we try to integrate them through virtual network nodes. So whenever we perform a measurement of user node, and it is being localized in, let's say, 1352 local reference frame and local reference frame 13421, we can basically use the same solution to tie together these two local reference frames. When we have more than several measurements, we can basically extrapolate the coordinates of our network nodes to the absolute positioning system solution. We perform some simulations, basically, with 100 network nodes, with reduced communication range and error of 2%, which basically corresponds to, if we do Wi-Fi, that would be an error of 2-3 meters. And we had some user nodes going through that network, which allowed us to incorporate absolute positioning solution into our network. So basically that's how simulation looks, and we just launched through them some in linear trajectories several user nodes. So through iterations we can see that network converges. It doesn't reach the full convergence of a network because some nodes cannot form tetrahedrons and cannot form local reference frames. This can be helped with these virtual nodes, but in general we achieve pretty good result in the propagation of our absolute positioning system solution. Yes, so the next step for us is trying to publish now a new approach how to use dynamic parameters of user nodes and how to incorporate them to use the movement information on the movement. And basically afterwards we'll try to create a full identification solution for Internet of Things. Yes.
Thank you, Katerina. It's quite interesting. And now we have time only for such short questions. Not for discussion.
Just a note, do not discard time of arrival, because if you are using time sum of arrival and it is the same node, actually ellipsoids turns into the sphere.
No, I'm not discarding it.
Regarding microelectromechanical oscillators, now they are gaining in price, and actually it is cheaper to buy a MEMS oscillator than it is
how much cheaper
for the crystal. Unless you are talking about chip scale atomic clocks.
Yeah, I was talking about chip scale atomic clocks.
But those are not MEMS.
Ah. Well, yeah, technically no. Just, yeah, thanks.
Maybe someone else. No, okay. It's good that we can go to the next presentation. Thank you again. It's work from Latvia.
Yes.
Yannick's will present as it. Okay.
Okay. Good morning, ladies and gentlemen. I'm Yannick Achen from Riga Technical University. So it's best. In my paper, which named Development of V2V and GPS-based collision warning algorithm for uncontrolled intersection, I tried to connect together two systems. One of these is GPS, global positioning system, and second system is V2V, vehicle to vehicle. This is information exchange between cars. The main aim was to create a warning algorithm to improve road safety, road traffic safety. As you know, now it's high development in the intelligent traffic system is always anywhere, but road traffic safety is very serious problem. To improve it, I propose the collision warning algorithm. One more. Exchange of information required for algorithm is achieved by means of vehicle-to-vehicle communication system. Vehicle-to-vehicle is from United States abbreviation, but in Europe is car-to-car, C2C. It's better for European country. Physical and data link layer are regulated by standard. These series. And message contents, intervals, and priorities defined by standard. This. I use here in my algorithm so-called BSM or basic safety message. This is from this standard. To establish or determine a safety criterion, it's worthwhile to present a car not as a single point, a point with, which is consigned with a GPS antenna, but a certain rectangle that will display not just the external dimensions of the car, but also the preset or determined safety zone. There are two reasons why we use this model. The first reason is that placement of GPS antenna and overall size of the car is known. And it's very easy to share this information between all participants of road traffic using V2V. Then we have to is the possibility to establish safety criteria. The main prerequisite for prevention of motor vehicle collision is that there must be no simultaneous overlapping of the projection of two vehicles along the coordinate axis. Or it's possible to establish it mathematically. The first step, we create function s and x and s, y, y, s. That's a letter s from safety, s. We create these functions and use these mathematical expressions. And safety criteria is this mathematical expression have to be everywhere and always. So there are a lot of scenarios on the road. One of these is very known and very often. This is forwarding through intersection, through unregulated intersection in straight, the first, and to to the writing to the left. This will be the second from stop position. Like here. And now, very simply, we create motion equitation for first car, then more equitation from second car, and create these functions. This will be which were before, and simulating this process, analyzing during the time. This is result. If here is the vehicle parameters with speed, acceleration. Some words about acceleration. Car's acceleration is from stop position. This acceleration depends on not only car's parameters, but depend on weather conditions and depend on drivers' psychophysical conditions. Here is acceleration 1.9 meters second. This is not very quickly, but average. If you can see here that dependence of these functions on graphs. Here is everywhere and every time moment is this our expression is true, and result is that we have proposed that intersection passage will be safe. So if we reduce starting acceleration twice, this is possible collision zone. And probably will be collision. The second, turning left. So, and in my simulation is only one car. Sometimes it's car this, but here is only one car. Here, the trajectory of movement of the car through the intersection with turning left. Change the course angle and linearity speed of the car. Now the simulations results. This with acceleration 1.9 very safely, and second, when we reduce starting acceleration, there is possible collision zone. So it's possible to analyze this this mathematical expression for all pairs of car which is on this square. And conclusion. So here was in this paper proposed a safety criteria. I want to tell you that this is only warning message. The final decision or final solution to do anything is the driver's solution. And the future work, I think that it's necessary to check it on the field test, on real conditions. So thank you. So the question, please.
We have enough time to discuss.
Yes.
Yeah, please.
Did you take into account the accuracy of GPS? Because it is, the GPS can make errors of 2 meters, 3 meters.
Yes.
And for a car,
Yes, I understand your
it's a
question.
problem.
Okay. This is a question about accuracy.
Yes.
GPS. Really, local GPS give the accuracy about 5, 10, or sometimes 15 meters. It's very bad result. We need to use GPS accuracy less than minimal distance between vehicles. So it's possible to use GPS with differential correction. It's real-time differential correction. Yes, it's enough. Color meter, it's good accuracy. Local is not very good, but with differential corrections, we don't need using phase correction. It's enough. Simple difference correction. Oh.
Please.
Yeah.
Have you considered expanding your security zone depending on the velocity of acceleration? For example, if a car is accelerating, you basically expand the safe zone because uncertainty rises.
Yes, from the first where is geometry? It's possible to use adaptive geometrical model. Yes, sure, this is not a problem. If the velocity or speed is higher, we have to...
No, but maybe there is no reason for that. I mean, it's good enough, that's why you didn't use it.
Difficult to say right now. I don't think about it, but this is a good idea. To less, to do less, sometime more to do bigger. This zone, this safety zone, this. Where is the? I don't think.
And maybe I'll ask such quite simple question. Is there somebody in car industry who knows about your work? Have you any project?
No, I'm alone. Because it's very difficult to...
It's their problem to find you.
All these works in car industry is private property of this industry, yes?
From
yours
is free, yes. Okay, thank you very much. Next is me.
So oh, yes.
Okay, it's my turn. This work is done in collaboration between Tallinn University of Technology and Aveiro University. And mainly all what I'd like to say is written on my slides. And no introduction, that we know that data processing is one of the most common procedures in systems, and mainly all of it is going to that we are like extracting items with the desired characteristics. No, this is work is proposed for real-time systems. It means that all processing has to be done as fast as possible, and to reach this high performance we use FPGA based systems. No, I think that's quite good solution for us. And then what we are doing now, first of all, we would like, there is such sequential channel, inputs are going one after another, and then we suppose that this data that are arrived from outside world, they are filtered, and only some of them are going to processing. And what is important, that processing is done in communication time. You see, it means that as the last data is arrived, then all processing is done, and the result is going to the output. Okay? And what are distinctive features of this work? No, first of all, as you saw on previous slide, we are trying to detect or filter this data, and we use one approach that was presented 6 years ago on FPL conference, but we adjusted for filtering. And then the second is the fast data processing based communication time network that allow both sequential data acquisition and processing to be done in parallel. No, such very simple examples. Maybe it's not so correct written, but it's not classical set, yes. But let's suppose that we have such input, one after another is going, and here we can see some values that are repeated, no? For example, 3 and 4. And in this case, we filtered them, and result is here. Yes. This filtering could be more complex. For example, we can take only some values from this. In this example, this values that greater or equal to 5 and less than or equal to 6 are discarded or blocked. And in this case, after filtering, we have this sequence. Okay. And there are 2 points in filtering. It's presented here. All the source items are included in the output sequence just once. Yes, non-repeated. If there are several items with the same value, then just one of them is included. Then, additionally, all predefined and explicitly indicated values are removed from the output sequence. It's data filtering, and this implementation of data filtering, as I told, it's done from our previous work. It was this work was done for sorting, but we adjust it for filtering. Idea is very simple. We have memory. Words are of size of 1 bit. Then every input data we consider as address in this memory. And you see, if some data is arrived, then 1 is written in corresponding address. If the next one is going, and if it's repeated data, then 1 is written already here. It means that this input data should be blocked. Here is a simple Cantrell circuit that because we have to make preloading to avoid undesirable values, but it's done only one time in the beginning of the process. You see. And it may look, if it should be blocked, it's blocked. If it shouldn't be blocked, then it's going to the output. it's no, we call it is filtering circuit. And then the second part, as you remember, it's communication time data processing. And this is in this work we demonstrate communication data processing on example of data sorting. We could take another task, but we've chosen data sorting. It means that we would like to get all the received data sorted immediately after the last item has been taken from the input, because it's communication time data processing. Here are the features of this processing, and again, sorted data can be transmitted almost immediately after receiving the last input item. You see? As we receive the last item, we are ready to present the result. Okay, again, some very simple introduction to our this second part of our system. I think that you know this. It's very old notion of comparator, this one or this one, and you see the two inputs. Then maximum, greater value is going to higher position, less is down. And in our case, we use such so-called networks of such comparators, or sorting network. And now it's interesting that now it's quite popular. Again, the first works about sorting network were done by Knut in this Art of Programming. You know, this famous book. It's done, I don't remember, but more than 30 years ago in any case. And now, because FPGA are very good for this parallel work, then they are again returned to consideration by this design community. And look, what these are comparators. Let's say this is input data. Then after first stage, something is changed, some order is established. The second stage, again, and if no swap is done, then we have this already sorted output of data. But look at that, any level. This is in green, it's the same, and any level can be reused. And what we do in our works, usually, we use this feedback here. Feedback, and enable here is equal to 1 if there is at least one data swap in the second vertical line of comparators. Else enable is 0, it means that all is done. Okay. And now this is circuit that we use in our work. It's totally about the same as it previously. Idea was presented. We see here this feedback, and as soon as a new item is received, it will immediately be placed in proper position. Here, this registers for writing of these data that are going from filtering subsystem. Yes, and as soon as a new item is received, it will immediately be placed in proper position of the produced sorted subset that is composed of all previously required items. So, okay. Now I return back. This is our data filtering. Remember, subsystem real-time accumulator sorter that I told just now. And any pre-filtered data item received on the input can be immediately accommodated, subset, and so on. It means that it's going in communication time very fastly. Okay? Implementation in hardware, as I told, we use FPGA. With FPGA, it's very convenient to work now because there are different prototyping boards. In this work, in our this paper, for this paper we use this Nexus 4. It's very cheap prototyping board. I attract your attention to price of this prototyping boards. They are very cheap, and often they are very powerful. Okay, and experience have shown that each coming data item is handled with the same time that is required to read data from the dual port RAM. That's what this is. I'd like to attract your attention that the size of data M is 16 bits. You remember this filtering, where is input as address. 16 bits. No, it's not so small amount of bits. Yes, but we need only one built-in FPGA RAM in FPGA, but there are hundreds of these RAMs in such normal FPGAs. In our case, it's very simple. But for this simple board, Nexus 4, more than 1,000 data items can be handled even in this relatively simple FPGA. Okay, and conclusions. Yes, no, it was the work was devoted to fast processing of non-repeated values, some of which can be discarded. I'm sorry, on request. The emphasis is done on real-time applications in which data items have to be received and processed within minimal possible time. The proposed solution modeled and evaluated in software, and then was implemented in hardware. No, and as usual, experiments have demonstrated that all is working and all is good for the decision of our task. I think it's all. Thank you very much. Thank you. Short questions.
Sorry, you had on slide number 12 written that it's 16 bits.
Yes.
But before there was, you said the word is 1 bit. What do
you
mean by that word?
16 bits. I will come back. 16 bits is we can see it as an address of this memory. But memory words in memory of 1 bit. So 1 bit. But
1 bit is 0 or 1?
Yeah, 0, 1. But there are 2 power 16 places.
Yes, but if you have the word of 1 bit, so you have either 0 or 1. So
yeah, 0, 1.
Yes, so
if data that are on this address lines was received previously, then in this memory there is already one.
Oh, you just
yeah. Well,
okay.
That is why it's such address based.
Okay.
It's a quite simple idea, but we have quite many references on our work. It's working. And there was such simple FPGA. It's enough because FPGA has very good resources. Okay, thank you. And now, who is the next?
working.
Okay, thank you for the presentations. Thank you for the introduction. My name is José Miguel. I'm working in the Kaunas University in the south of Spain. Right now I am a PhD student. We present my work with the title IMAS, an industrial metamodel for automation system. This is the overview: software development in industrial automation system. MDE, industrial environment, the OPC standard, IMAS, and modeling a climate rule with IMAS, and the end, the conclusion of the future work. The software necessity in the industrial system are increased year per year, at point that the software system is a very important part of the software of the industrial environment, like electronic system or pneumatic system. Also, the apparition of the new paradigms like Industrial 4.0 has accentuated this software necessity because we need to integrate the IT system and the industrial software system. And the traditional technique for develop software could not solve this necessity, so we need to find new paradigm to solve this necessity, like MDE. Model-driven engineer. The main concept or the main idea behind MDE is the abstraction. The abstraction could be of the way to resolve a complex system. How can achieve the abstraction using models and metamodels. But what is a metamodel and model? A metamodel defines a language, a common language, for construct or for build the abstraction, and this construction of the result of this construction is a model, and we can say that a model is conform and this metamodel. Okay, but for deployment this paradigm into the industrial environment, we need some standard or some platform that supported this paradigm, and one of them could be OPC UA standard. The OPC UA standard is the last specification of the OPC foundation and has two main pillars: the communication model and the information model. The communication model is out of scope of this work, but the information model is very important for us that we can see after. Okay, IMAS is an industrial metamodel that we see before. It is a specific metamodel conceived for develop and deployment on industrial automation system. IMAS provides a common system, a common concept that we can deploy this concept in several parts of the industrial system that we can see after. And the most important for my point of view is that provides a systematic methodology for organize the signal or the devices in the industrial system. Okay. And another important point is MAS is based or is extended the information model of the OPC UA. Okay. Do we have the abstraction level of the IMAS? We can deployment IMAS in the OPC UA, of course, and the industrial device also. This is the architecture of IMAS. In this work, we are focusing in the layer 0 and layer 1. Is the layer 1, the abstraction level of this layer is different between of them. This is the most complex layer. Just now we are finished this layer, but when I working in this paper only have deployment these two layers. Okay. This is the information model of OPC UA, and this is the concept that we are using in IMAS. Okay, the most important concept is object type. We can see here the extension of the IMAS coming from the object type. We have two concepts or two objects, PLC data and simple object. This is the element of the layer 0. Also, we can see here the element of the layer 1. In this level, we are focusing in the input and output of the devices the analogic and digital input and output, and this element allow us abstraction of this type of input and output. Okay. Right now we are focusing in deployment IMAS into the OPC web server, and for that, and for this, we need to first we need to translate the metamodel of IMAS in the XML file. After that, we need to compile this file, and in our case, we are developing a specific OPC web server in .NET because for all the products that we have in the market are not very. For the point of view of metamodel is not complete, the product, the market product or the commercial product. So at the end, we decide to develop our OPC web server. Okay, this is the correlation between the concept of IMAS of the layer 1, layer 0, and the translation in the XML file for OPC web perspective. With this is more or less directly. Right now we are focusing in the deployment the IMAS into the industrial devices. In this case, we are using the Siemens PLC. It's not directly translation because this element we need to deploy for a structure regarding of type of data that we are using. In this case, we are using UDT, is data type defined by the user. And this is the first step. And the second step is organize the DB data block into the PLC with this UDT that we are defining before. Okay. At the end, we need to provide our metamodel in a real case. In this case, we are using a climatic rule controlled by the Siemens PLC. And these systems are divided in two subsystems. The first subsystem is here. It's the perturbation subsystem to introduce perturbation in the system. And the second subsystem is the temperature regulator. With this system, we can regulate the temperature into the box. This is the model, and the other is the model for the system. This is the result because we have IMAS deployment in the OPC UA. We have the metamodel in the OPC UA server, and we can create model using this metamodel. And this is the result of the point of view of the OPC UA client. We can see here all the objects that we have defined in the model. And this is the result of deployment in Siemens PLC using UDT. Okay. This is how finally the conclusion, the future work. IMAS provides a novel approach to simplify the description of the industrial process. And the application of MD in several parts of the industrial system achieve us to use the same concept, because at the end, in the OPC way, we have the same model that we have in the PLC on the industrial device. And how Future works, we want to define automatically translation between the model and the deployment platform. For example, we are thinking to create automatic rules for take the model and create the XML file. Another important point for us is implementing the behavior of DMAS using some standard like ISA H8. Okay.
We have enough time for questions. But it wasn't so easy to follow the slides. Okay. And maybe a few words. I've seen there was one example of implementation, but have you another example?
Another example. This year we are presenting on the special Siemens work in Spain, so with another university, and I use IMAS for develop a special packaging system and it's working fine. I'm working in our laboratories in automation, and in this year in HVAC system, I start deploying IMAS and working. So I think it's very, it's a way to organize the signal in the industrial system.
It means that you are lucky.
Yeah, yes.
Okay, maybe somebody would like to ask. Nobody? Thank you again. We were too fast because we missed the presentation of Andrews from Lithuania. Yeah. It's a very complex topic. But if you read it.
Okay, hello everybody. I am Andrius Lučka from Kaunas University of Technology, and my PhD work will be to create a mathematical model which could control granulation process of fertilizers. And one of the topic is that I need to create a system which could control, which could measure the particles of fertilizers in real time and enough with good accuracy. In short, I'll talk about fertilizers, particle size distribution, main parameters, and image processing and mathematical model. Firstly, I should start talking and say I started talking and said that the increasing number of people means higher demand for food, and but threats in agricultural production, such as pests, loss of soil fertility, or lack of nutrients, may result in low percentage for plants to harvest. All nutrients in our food are come from the soil, and the farmers need to work with healthy soil that we could get the food with full of nutrients. These nutrients are potassium, calcium, nitrogen, and other. And fertilizers will affect the general health of the plant. The benefits of granulated fertilizers. The effect of granulated fertilizers lasts longer than liquid fertilizers because the solid is absorbed in a slower rate. An advantage of slow release granulation granulated fertilizers is that you don't have to apply it very often. Also, it occupies a smaller volume. It is a better solution for storing. Has a better aerodynamics for spreaders, and some other more accurate fertilization, safe use of feed granules. Granulation is the process of combining particles together by creating bonds between them. Bonds are created by compression or by using a binding agent when we are talking about wet granulation. And one of the most important parameter of granules is granular size, average of it. The name of this parameter is D50. And for that parameter, the biggest impact have moisture. That means that when we have too much moisture in granulation process, we will get too big, oversized granules, and in our way we get undersized. That means that we will get decreased manufacturing capacities and increased energy consumptions, because we need these granules to reworked. Particle size distribution is very important in factories because it gives information about the quality of these particles, and there is a few parameters. One of them is D50, the average of particles, and another is GSI and UI, granulometric spread index, which give information about the spread of the granulation, the accuracy of possibility to feed granules uniform, and uniformity index gives us information about the variance in particle size distribution. At the moment, factories using CU's methodology. That means that the measurements are performed only every few hours, and you can't see the differences in real time. How it's measuring the particle size distribution. Factories in laboratory using sieves. We have a few sieves with different hole size, and after some vibrations, we just weight the particles on different particles and get the distribution. If we want to control the granulation process, we need to get information on real time. There is a few indirect measurement methods which gives us quite accurate information. One of them with which I am working is image processing. I'm using a camera, and I could get particle size distribution. Here you can see that volumetric distribution is equal to the mass distribution, which you get the laboratory in the factory. And the image processing, I'm using only one camera. That means that I get a two-dimensional picture. So I need to approximate my granules, and the most accurate results will be get if I approximate it by ellipse. And after that, I can calculate the volume of my particles. Also, this measurement is not ideal. It depends on the granular size. If I have granules which are almost ideal spheres, circles, I could use only Hughes factor, one coefficient, which gives my opportunity to me to change the cumulative curve. Here you see the red one. Here you see a histogram of granules distribution, and the red one is cumulative curve, and the black one is measured with camera. And if you have the bigger granulars, better. You could use Q factor, which gives the opportunity to take the cumulative curve to the left or to the right, and that's enough. But if we are talking about the granulars, which size is smaller than 1 millimeter, we need to use some mathematical model which could help to recalculate our results. And one of the simplest model could be a least squares polynomial. And the main idea is to control the granulation process. We need to take samples at short time and measure particle size distribution. Also need to get moisture and temperature and some maybe other parameters which could be implemented in our mathematical model, and we can offer an operator to choose the most accurate parameters for controlling the granulation process. And in conclusion, is that the system method is widely used in factories, and indirect measurements enable us to implement, to automate the measurement process, and real-time measurements give us possibility to control the granulation process. At the moment, about 10 of the systems working in the local factories, and I'm testing it on the real production line. Thank you.
Thank you. Very interesting presentation, because it's, for me, it's absolutely new area. I was much knowledge. Okay, we have time for questions.
What is the average mean error, basically, from estimation to values on the work?
It's about from 3 to 5%. But if you're using, say, like we say that circle or arrow, you could get results which are very far from the real particle size distribution.
Well, 3.5 is good enough, right?
But if you recalculate it with mathematical models, you could get almost ideal.
Okay. Somebody else? I will ask because it's interesting for me. You mentioned that this should be working in real time.
Yeah.
It means, does it mean that you need to optimize your models or to something to accelerate and so on? Which tasks were decided to reach this real time?
Real time is that we get the correct sample and get the PSD, and also measure the moisture, temperature, and these data could be analyzed in real time.
You see, it means that there were weren't problems to calculate more faster and so on.
This is, we are talking
to
about
optimize.
yeah, but we are talking about from 3 to 6 to 8 minutes.
You had
That's
enough time.
Yes.
Okay, thank you. And now the last, not the least, presentation. It's a presentation from Turkey. Abdullah will tell us about the deep neural network classifier for decoding human brain activity based on magnetoencephalography. Okay.
Thank you for being here today. I am Abdullah Çalışkan from Erciyes University from Turkey. I am here today to talk about a deep neural network classifier for decoding human brain activity based on magnetoencephalography. I have divided my presentation into four sections. First section, magnetoencephalography. Second, method. Third, experimental result. The last one is conclusion. So, as I mentioned, the first thing is about MEG signals and magnetoencephalography. MEG signals is produced by the brain. As you know, the brain is a very powerful and very complex organ which make us human being. It is responsible for our thoughts, for our feelings, for our memory, for our perception, and everything else has happened. And therefore, it is great to know how it works. So there exists lots of several brain imaging techniques to understand how it works. First, one of the most important brain imaging techniques is MEG, magnetoencephalography. Magnetism, and encephalography means brain, graph means images. Magnetoencephalography means magnetism of the image of brain. And let us to pass the other section, brain decoding. Brain decoding, by analyzing human brain, scientists may able to decode human brain thoughts, their dreams, even their perceptions. Therefore, in our study, we try to decode the human brain by using a simple visual stimulus. You see a subject. When a subject is presented a visual stimuli inside the brain, there will be a pattern of the recorded signal, and according to this pattern, we try to predict subject C face or Scrabble face. However, this process is very complex, and to analyze the Mach signals is very hard due to Mach signals has lots of time series. Besides, it's corrupted with significant amount of noises. Therefore, in order to analyze the Mach signal, you need three main process. First is feature. First, you need pre-processing steps and feature extraction process, and the last one is the classification. So Mach signals need significant classifier to decode the human brain activity. In our work, we focus on to design a good classifier, and it is a very popular classifier, deep neural network classifier. Our classifier, the pattern of the brain signals is sent to classifier, and classifier predict people, subject, see Scrabble face or non-Scrabble face. And the proposed DNN consists of two parts. The first part is autoencoder and softmax classifier. And DNN classifier offers the ability of autoencoder to produce leaf feature from raw feature, and the capability of the softmax classifier to classify the labels correctly. And the main part of the DNN network is autoencoder. Autoencoder is a simple neural network actually. it consists of two layers. First layer input layer, second layer is hidden layer, the last layer is output layer. The actually autoencoder has two parts. First part is encoder parts, the second part is decoder parts. Encoder parts connect to input to hidden layer, decoder parts connect hidden layer to output layer. Objective function autoencoder actually is similar to a normal neural network, feed-forward neural network. We are trying to between the system output and label to decrease the error, and these the weights which are tried to tune. I will not explain detailedly this part due to limited time. Softmax classifier. Softmax classifier is a supervisor layer of deep classifier which generalizes the logistic regression. It is a simple classifier and very suitable to deep neural network. Training of the NN classifier has three parts. First of all, you have to train the autoencoder, and the train autoencoder of the hidden layer send it to softmax layer to make prediction, and then encoder part autoencoder is taken and softmax layer is taken, are combined to produce the DNN network, and after this these weights can be tuned one more time by convenient optimization algorithm. In our case, we use LBFGC algorithm, limited memory algorithm. The other section is experimental results. The human brain decoding with max signals is achieved by using the train DNN classifier. We try to a subject see face or Scrabble face. A data set is originally by created 6 and modified it back the MAC 2014 computation. Data set is contain 16 subject with 563. As I mentioned before, max signal have 206 channel. Training of DNN, the parameter of the DNN is chosen just like, and we have nearly 10,000 example and 2,000 features. It's a very large data set, and it has has several features. We use 5 cross-validation techniques with 30 independent runs to analyze, to verify our methods. We compare the DNN classifier with traditional methods, including SVM, naive Bayes, Kaunas boards, and decision tree. Results are analyzed over obtained rates. The obtained results are supported with statistical analysis, including the Mann-Whitney U-test and ROC-RAFT. And this, as can be shown in this figure, for 30 runs, accuracy of the DNN is each time has better performance than the other methods used in this paper. And you see the mean value of the 30 runs. DNN has the better average rates. DNN has the lowest standard deviation. This means that DNN is more stable than the other methods, and also DNN has the best AUG value. What means AUG value? You see DNN with blue curve. Area under the blue curve is largest for DNN. it has the largest value. Arc value is approach to 1. This means your classifier is approach to perfectness. The last one, the statistical results. We use to verify our experimental results. We use the DNN classifier. We use the Mann-Whitney U-test to compare the DNN with the conventional methods, and the results show us DNN has the better performance and has better significancy with p-value is lower than 0.05. And conclusion, in our work we have presented a very efficient classifier for decoding human brain activity from max signals. Our simulation results demonstrate that DNN classifier is better than the other methods used in this paper. As a future work, other possible application of proposed classifier should be explored in both clinical and non-clinical domain, and our proposed classifier can be used to analyze different cortical regions of the brain. Thanks for listening. And question?
Now time for questions.
Sorry?
How did you select from your data your training set to train your algorithm and the validation set, and what was the ratio?
Actually, we selected for the DNN is a very popular method is now. The other method is applied to analyze such things. However, the DNN network is not used before. We tried to make something different, and we obtained good results.
No, especially for how you select your data and separate it into training, validation, and testing, because the results you showed only shows one. So basically, we are asking which part of.
We use 5 cross-validation techniques. We divided our data set 5 parts, and 4 parts used for training, and the remaining part for testing. And this process is repeated for 5 parts. Yes, of course. Therefore, we can conclude it.
Can we ask you about the data? Because I understand this is not your data, you obtained it from some
Yes,
database,
yes,
right?
yeah.
Do you have some information about signal-to-noise ratio of this magnetic?
No, actually, I don't know.
A very silly question. It's always this neural networks. They are so complex to implement. They're so time-consuming and so on. Maybe you could do it without neural networks. Another tool.
If we use normal neural network, it cannot handle this huge data sets. Actually, you have to wait too many times.
Okay, maybe somebody let us, because Abdullah, your presentation is concluding our session, and not only our session, but the conference, because at least in this room 8. Okay, thank you very much. Thank you.